There we go. All right, couple of announcements. Let's get started with class now. All right, the next Achieve homework is due Monday. That's already posted for you all. So that is the rest of Chapter 4. We'll finish this on Chapter 4 on Friday. Our midterm exam is next Friday. So this is, I'll have more information for you on Friday in 2 days. But this is an all multiple choice exam. There will be about 30 questions. Each exam is worth 60 points, so it'll be about 2 points per question. This is cumulative. So this exam and our final are cumulative. That means that it will cover content that we've learned since the beginning of the semester. So definitely chapters 1 through 4, maybe some of chapter 5, depending on how far we get through chapter 4 this week. But I'll let you know for sure. It would only be a little bit of chapter 5 since we won't be covering that much before the assessment. So since it covers chapters 1 through 4, you want to make sure before the assessment that you're going back and reviewing content from chapters 1 through 4. You might start with chapters 3 and 4 since we haven't had an assessment on chapter 3 or 4 yet, and then go back and review chapters 1 and 2. The good thing about chemistry is what we've learned in chapters 1 and 2, we haven't completely diverged from. So a lot of what we talked about in the most recent 2 chapters is related to what we learned in chapters 1 and 2. So all of that to say, keep in mind that all of that will be on the assessment. The chapter 3 and 4 learning curves are available on Achieve. Those are due at the end of the day, October 20th, if you want the extra credit point for each of those. All right, at the end of class last Friday, we were talking about naming acids. So there's really 3 different patterns for naming that we've talked about. One is when we have a binary acid, so hydrogen, and then one other element. Chlorine and sulfur are shown on here. When that is the acid in aqueous solution that we're talking about, we have hydro as the beginning of the name, the root of the other element. So for chlorine, that's chlor. For sulfur, it's sulfur. And then ic acid at the end. So binary acid, 1 hydrogen, 1 other element. This is the pattern that we follow. And then if we have hydrogen with a polyatomic ion, we've talked about naming acids if we have a polyatomic ion that ends in ate, like nitrate or sulfate. When those are with hydrogen in aqueous solution, they act as an acid. Nitrate with hydrogen in solution is nitric acid. Sulfate with hydrogen in solution is sulfuric acid. So we add the ic acid. We change the ate to ic acid. And then similar pattern if we have polyatomic anions that end in ite, in ite, like chlorite, those become chlorous acid, so OUS acid. Phosphite, phosphorus acid. So at the end of class, we didn't have time to review all of these, but this was the slide that we ended on, so I'll just go through these right now. This first molecule, we have hydrogen with nitrite polyatomic anion. So nitrite becomes nitrous acid. So this is nitrous acid. Oops. This is why, another thing I forgot to mention is I posted an announcement, I believe it was on Saturday, that has information about some things that are useful to just memorize for our class. So one of those things are the names and formulas of most of the polyatomic ions. Having the name and formula memorized will help you solve problems where you're applying that knowledge. Here's a good example of that. If you knew that NO2 was nitrite, you knew that to name the acid version of that anion, you change ite to us acid, then you can name the acid, nitrous acid. Now this next one, HCN, this doesn't follow the rules that we talked about, so you can, I'll write the name of it, but don't worry about this one. This is hydrocyanic acid. This, although we have a polyatomic ion, it follows the rules for the binary acids, so I won't ask you about one like this. Don't worry about this one for now. Next, we have hydrogen with a perchlorate anion. So the acid version, we change perchlorate to perchloric acid. Next, we have a binary acid. So hydrofluoric acid. Next, we have hydrogen with a permanganate anion. Permanganate becomes permanganic acid. And then the last one, we have carbonate anion with hydrogen. So as the aqueous acid form, it's carbonic acid. So the second one is, I don't even want to put a star there. This one's just different, special, don't worry about it. But the rest of them, all that we're doing is following the rules in the previous slides on naming acids. Given the polyatomic ion name, use the rules that are provided on the previous slide. Questions on any of these names? Okay, that concludes that section, and we're moving on to oxidation states and redox reactions. So we've talked about, the previous section was all about acid-base reactions where we transfer a proton, a hydrogen cation. In oxidation reduction reactions, we're looking at the transfer of electrons. So that's the key feature of oxidation reactions. So to determine which atoms lose or gain an electron, we calculate oxidation state. So we'll learn about how to calculate an oxidation state. That's a property of an individual atom. So individual atoms in compounds have different oxidation states. So we'll do that. And then we'll talk about how oxidation states change when we go through a redox reaction. We'll determine what gets oxidized, reduced, oxidizing agent and reducing agent, all of that we'll talk about. So oxidation reduction reactions are reactions in which an electron or more than one electron is transferred. So we have one species or one atom that loses electrons and another gains the same amount of electrons that are lost by the other species. When something, we're going to start with the gain of electrons first. When something gains electrons, remember electrons are negatively charged. So if you gain more electrons, you're getting lower in their overall charge, and we call that reduction. You're gaining negative charge. When you lose electrons, electrons are negatively charged, so if you lose negative charge, you are increasing in oxidation state, and we call that oxidation, is the increase of charge or loss of electrons. So oxidation states, which are also known as oxidation numbers, this is a type of electron bookkeeping, so a system to keep track of the electron transfer in redox reactions. Redox reactions is just another way to say oxidation reduction reaction. RED is short for reduction, OX is short for oxidation. So redox reaction is an oxidation reduction reaction. So we calculate or determine oxidation states for individual elements on their own, or when within a compound it's an oxidation state for one element. And then we have some rules here for assigning oxidation states. The first is that if you have a neutral element that's not part of a compound, so it doesn't have a charge, it's not part of a compound, that oxidation state is 0. If you have a monoatomic ion, so one atom that has a charge, the oxidation state is equal to its ionic charge. Now this is important. Sometimes oxidation states are equal to an ionic charge, sometimes they're not. So we can use these rules that involve ionic charges to determine oxidation state, but it's not a 1-for-1. They're not exactly the same thing. Rule number 3, the sum of all oxidation states for a formula is equal to the overall charge of that formula. So if you have a neutral compound, the overall charge of that compound is 0. So the total oxidation state of each element in the compound, if you add them all up, it should be 0. If you have a polyatomic ion, like nitrate, that has a -1 overall charge, if you add up all of the oxidation states of the nitrogen and the 3 oxygens in the nitrate, the sum of the oxidation states is -1, so equal to the overall charge. Oxygen typically has an oxidation state of -2. Hydrogen has typically an oxidation state of +1. So those are 5 kind of basic rules, and then a few more special rules. If there is a conflict between 2 rules, apply the rule with the lower number, ignore the conflicting rule. Applying the rule with the lower number means higher on the list. So we go with basic rule 1 and then move to 2 and then 3, 4, and 5. If we have a binary ionic compound, so 2 different atoms only, no more than 2 different atoms, one of them is a metal, then the nonmetal in that ionic compound has the same oxidation state as its ionic charge. After this slide, we'll do a few examples that go through these rules. And then lastly, fractional values of oxidation numbers are allowed. So we can have an oxidation state of +1/2 or -1/2. Okay, using these rules, let's go through these examples. This is an iClicker, so let's send that out. So determine the oxidation state of each of the following species, the atoms in each option. If you have an oxidation state of 0, input the number 0. If you have a positive oxidation state like +1, input the oxidation state as plus and then the number. If it's negative, do negative sign and then the number. So put the sign first. And if it is positive, include the positive sign. So let's spend a few minutes working on that. And then let me know if you have questions. You want to determine what type of element or compound, what type of species you have, and then apply the rule that applies to that. Oh, just do the oxidation, so you don't put stuff with the number. It's okay. If it's positive, do positive. Okay. Don't retype the element, just put in the value.
Like if it's like this, the bar
Like overall the components? Yeah, if there's a charge, like if the whole thing is an ion, there will be no.
Right.
Elevation out of charge. So yeah, that's what you would based on the period. In a neutral to solid sample of magnesium We'll do another minute or two. If you're finished, feel free to try out the next learning check. We'll do that one together, but you can get a head start. Also, exciting news, we're officially halfway through the semester. So there's 15 weeks in the semester and we're halfway through week 7. So already halfway through. Isn't that crazy? Goes by that.
And then it says, then we know that it's negative 2. So you can like write out the equation, add it to our
So magnesium, the first one, is a neutral charge. Phosphorus is the second one, and the so we use that also. Let's say one more minute. So when they're 6, when that time says 6:30. Yeah, chapter 4. You can still submit it if you say no.
Oh.
Oh, okay. In about 30 seconds, try to get your answer submitted. Ten seconds. All right, closing it here. I'm gonna see what we're thinking. All right, question 1. Okay, so quite a few put 0 for the oxidation state of magnesium, and then +2 was the second most common. So magnesium is in the second column of the periodic table. So if magnesium is in an ionic compound, we can assume it has a charge of +2. But magnesium here is not in a compound. It's magnesium, it's a monoatomic, or it's just an element on its own. It's not even an ion, it's an element on its own. So here we follow the first guideline, which says if we have an element that's neutral, not in a compound, its oxidation state is 0. So this one is 0, oxidation state. Next, we have phosphorus with a -3 charge. Now here we follow the second guideline, which says if we have a monoatomic ion with a charge, then its oxidation state is equal to that charge. So here we have a -3 oxidation state, which looks like that one was pretty good. And then question 3. Okay, pretty good on question 3 as well. So here we're using 2 different guidelines. First is that when we have, it's the second one here, we have a binary ionic compound, 2 atoms, one of them is a metal. The nonmetal, so in this case chlorine, has an oxidation number equal to its charge. So chlorine has an oxidation number of -1. Now we have to use guideline 3 here. The sum of the oxidation states in any formula is equal to the overall charge on that formula. Here we have no charge specified for iron chloride, so we can assume the overall charge is 0. We have 3 chlorines with a -1 oxidation state. We have 1 iron, so the iron must have a +3 oxidation state. Okay, before we move on, questions on any of these? Yes. Yes, so that is the second rule here. If you have an ionic compound, a metal and a nonmetal, and there's only one element as a metal and one element as a nonmetal, so not a polyatomic ion, then we know that a nonmetal, so chlorine in this case, has an oxidation number equal to its charge. So we assume chlorine has a -1 charge. It has a -1 charge. We can apply that as the oxidation number as well in this compound. Okay, let's go through. Now we have a polyatomic ion. The overall charge of this nitrite ion is -1. So we need the oxidation state of nitrogen and of 2 oxygens to equal -1, because that's the charge of the compound. In our guideline, we have that oxygen typically has a -2 oxidation state, and we have 2 oxygens. And then we don't know the oxidation state of nitrogen, so we can put in a variable here. The oxidation state of nitrogen plus the oxidation state of both oxygens should be equal to the overall charge of the ion, which is -1. So we can solve this equation for X. X is the oxidation state of nitrogen. We have X -4 equals -1. So X equals +3, and that's the oxidation state of nitrogen. Yes?
Can you explain the last one one more time? Like on the other pages?
The iron? Yes. So when we have an ionic compound that has 2 atoms only, a binary ionic compound, we can follow the second rule on this page. In binary ionic compounds with a metal, the nonmetal, so in that compound that's chlorine, has an oxidation state equal to its charge. Based on the periodic table, chlorine's in the 7th column, so we say it has a -1 charge. So we can say that's its oxidation number in a binary ionic compound. So knowing that chlorine is -1, now we're using the same process as finding the charge of iron. Chlorine is -1, we have 3 of them, so that's -3 overall. And the overall charge of this compound is 0, so if we have -3 total for the negative oxidation state, then we need +3 for the iron to balance it out. Okay, we have a few more examples. Let's do iron oxide here. This is a neutral. We're assigning oxidation states to all atoms here. We have a neutral molecule. So the sum of the oxidation states should be 0. Or let's just start with 0 equals. Not oxygen, that's a 0. We have 2 irons. We don't necessarily know the oxidation state of iron, so we have 2 times some variable plus 3 oxygens. Oxygens typically have an oxidation state of -2. We can assume its oxidation state is -2. So if we solve for X here, that's our oxidation state of iron. Solving for X, you would get iron has an oxidation state of +3, and we know oxygen has an oxidation state of -2. Now we're working with compounds that have more than 2 atoms. This one is a I-clicker as well as the next one, I believe. Yeah, the next 2 are I-clickers. When you're working with sodium and also potassium in this last example, we can assume the oxidation state is +1 as for both of these. So you'll use that in the I-clicker question. You are assigning the oxidation state for carbon in the second one here, and then vanadium in the third. So I'll give you all some time to work on that. Vanadium. Oh, I've been saying vanadium. Vanadium. So all of these have an overall charge of 0, all of these compounds. You know oxygen should be -2. In this first one, sodium is +1. We'll be solving for carbon.
Yeah, so it'll be 0 equals. Yes, for the second. So, yeah.
2 plus 2 minus 6.
Yeah, so it will be 3 minus 6.
Yes, 2 minus 6.
Yes. +4. Put the sign first. Plus whatever value. Doing a number and then the sign is also correct. Just when we use I-clicker, I have to put in one correct answer. So I put them in as having the sign first and then the value. If you are done with this page, just because I see some of you have submitted, I'm still going to give you all a few more minutes, but if you are done, you could go to this page and assign oxidation states to the elements here. We'll do that as a class, but just to give you all something to work. "15 seconds here. Make sure you have an answer submitted." All right. All right. In this first sodium carbonate, I think that's carbonate, we have sodium has a +1 charge, or +1 oxidation state. We know oxygen has a -2. The overall charge is 0, so here we're just solving for the oxidation state of carbon. So we can have 2 times the oxidation state of sodium plus X for the oxidation state of carbon plus 3 times the oxidation state of oxygen, and all of that is equal to 0. If you solve for X, we have carbon's oxidation state is +4. So we have sodium +1, carbon +4, oxygen -2. Next we have vanadium, which we don't know the oxidation state for, so we'll put that as X. We have 3 oxygens, which have an oxidation state of -2. And we have 3 hydrogens, which have an oxidation state of +1. So we set all of that equal to 0. Solving for X, we get X is equal to +3. So vanadium plus 3 oxidation state, oxygen minus 2 oxidation state, hydrogen plus 1 oxidation state. Last example here, we have 2 potassiums with a plus 1 oxidation state, 2 chromium, we don't know the oxidation state, so we need 2x because we have 2 chromiums. And then 7 oxygens, 7 times the oxidation state of oxygen, which is -2. Set all of that equal to 0. And you will calculate x is equal to +6. So chromium plus 6 and oxygen minus 2. Questions on any of these?
On the test, is it gonna ask us, like, for example, to do like CR, like to find which exact element? Or are we gonna, like,
Yeah.
what it did on that?
As opposed to finding each individual one? I mean, it could ask both. But you wouldn't know chromium if you didn't know potassium and oxygen. So you'd have to know those as well. Yeah.
So potassium charge is given, right, from the question?
Okay. So I don't know if we have any examples here. We don't. But in different compounds, the same element could have a different oxidation state. So in oxidation reductions, an individual atom's oxidation state is changing in the reaction. So remember, if an oxidation state increases, that means that that atom lost electrons, and we say that's oxidation. If an oxidation state decreases, so becomes more negative, that means that atom gained electrons, and we call that reduction. So the substance that is oxidized, that loses electrons, is giving electrons to the substance that ends up being reduced. That's the substance that gains electrons. Then I already mentioned this earlier, that oxidation reduction reactions are also called redox reactions. So we have a substance oxidized, we have a substance reduced. The substance that is reduced, let me go back real quick. The substance that is reduced gains the electrons. So we can call this substance the oxidizing agent. So this is the substance that's taking electrons from the element that's oxidized. So the species that's reduced is the oxidizing agent. That's that first bullet point here. Species that has the element, species would be, if you have a compound, one of the elements in a compound gets reduced, that whole compound is the oxidizing agent. That's what the species is. So the species that has an element that is reduced is called the oxidizing agent. And then vice versa. The species that has the element that is oxidized, so the element that lost electrons, that's giving electrons away, that whole species is called the reducing agent. When we're talking, oh, go ahead.
Wait, so how do we tell if an oxidation state increases or decreases?
We will do that on the next slide, but what we do is find the oxidation state of all of the elements in the reactants, oxidation states of all elements in the products. We identify which element changed oxidation state. If it increased, it's oxidation. If it decreased, it's reduction. When we're talking about oxidizing agents and reducing agents, that's the whole reactant, not just the element that's oxidized or reduced. So here's an example. If we have a reaction where magnesium chloride is a reactant, and then magnesium metal, neutral magnesium, is a product. Magnesium starts with a +2 oxidation state, ends with a 0. So So magnesium element is reduced, its oxidation state decreases. That's the individual element that is reduced. But the oxidizing agent is this whole molecule. So oxidizing agent is the whole compound. So let's do an example. Put all of this into an actual reaction. We're going to find the oxidation states of every element. We will identify what is oxidized, what is reduced, what is the oxidizing agent, what is the reducing agent. I feel like I'm responding to Jeopardy questions. And then if all electrons, this is another condition for redox reactions, the number of electrons lost by whatever was oxidized must equal the number of electrons that are gained by what is reduced. So we'll determine if number of electrons lost is equal to number of electrons gained. Okay, so we'll accomplish all of that for this reaction. First thing we need to do is assign oxidation states for every individual element in the reactants, every element in the products. We have aluminum, which is a solid. It is an element on its own, not in a compound, doesn't have a charge, so its oxidation state is 0. And I'm just going to put the oxidation state below aluminum. For chlorine, we'll put it above the atom, and that will help our notes just be more organized. You could put them all on the bottom, it's fine. Chlorine is another element. It's on its own. It's not in an ionic compound. It's not in a binary compound. There's only one element there. So it also has an oxidation state of 0. Now when we go to aluminum trichloride, this is a binary ionic compound with a metal. So our rule, one of our special rules, is that when we have a binary ionic compound, the nonmetal has the oxidation state equal to its ionic charge. So chlorine is the nonmetal, its ionic charge is -1. We can also apply that as being its oxidation state. So chlorine oxidation state is -1. We have 3 chlorines. We only have 1 aluminum. We need the overall sum of oxidation states to be 0 because this is a neutral compound. So aluminum in aluminum trichloride must have an oxidation state of +3. Questions so far before we move on? Yes. Aluminum is +3. It's the same rules as the question from earlier, iron chloride. We know that chlorine in an ionic compound with a metal has an oxidation state equal to its ionic charge. Chlorine's in the 7th column, has a -1 ionic charge. There are 3 chlorines. There's only 1 aluminum, so to balance it out, we have a +3 for aluminum. Okay, now we look at each individual element. So we look at aluminum as starting material and aluminum in the product. Aluminum's oxidation state went from 0 to +3. So we have an increase in oxidation state. This is the element that is oxidized. So we can say oxidation occurred here. It lost electrons, became more positive, oxidation. Chlorine did the opposite. Chlorine started with an oxidation state of 0 and became oxidation state of -1. So it has reduced. So we say reduction occurred. It gained electron in electrons, so we have a reduction in its oxidation state. If you can identify an element that changes in oxidation state where one is oxidized, one is reduced, then you have a redox reaction. When we're labeling what is oxidized, that is the individual atom. So what is oxidized in this case is aluminum. What is reduced is chlorine. The oxidizing agent now is the starting material, whole compound, excuse me, that causes another atom to be oxidized. So it's the compound that takes electrons. Chlorine became reduced, or chlorine is reduced. So chlorine, Cl2 gas, is the oxidizing agent, so that whole compound. That means that our reducing agent is the compound for which the element in the compound is oxidized. This is the compound that provided electrons. So in this case, it's aluminum solid. Okay, so we've identified all four of these parts. Last goal is to determine if the number of electrons lost is equal to the number of electrons gained. It appears that chlorine gains 1 electron, aluminum loses 3 electrons, so that doesn't appear to be equal. But we have to take into account how many atoms are present. My throat's dry after 2 lectures. We have 3 Cl2 molecules. So we have 6 chlorines. I'm going to avoid talking for a second here. Six Cl atoms, each one gained 1 electron, so that's a total of 6 electrons gained. Aluminum, we have 2 aluminum, taking into account the coefficient. Each loses 3 electrons. So we have 6 electrons lost. So electrons lost equals electrons gained. So this is a balanced redox reaction. Questions on this slide? Yeah.
Why is the Cl the one that's gaining? Shouldn't the Cl be the one that's losing?
Great question. It's called, I think the confusion is with the words. So we are reducing chlorine by its oxidation state, so becoming more negative. To become more negative, you have to gain electrons. Good question. All right, we'll be done here. We'll finish up chapter 4 on Friday. I do have office hours today at 1 if you want to stop by. I'll have my door open.